All right, how's it going, everybody? It is Tuesday of week 9. We're recording our first video here of the week. I've been having a little bit of technical difficulties here the last couple days. I was having a certain set of issues yesterday that prevented me from actually creating the video at all yesterday. And now today I've been kind of screwing around with Twitch for the last 20 minutes here. I cannot, for some reason, seem to actually connect and live stream this for some reason. But I'm still able to use my software to make my video. So I'm going to see if I can get our streaming issue worked out so that I can actually be live for tomorrow's video as well. But as it goes with these things, I guess we'll see. The list of things that is working different for me every day is getting long. So I would like to guarantee you something, but I can't. So at least I can still make this video right now. So here we are. So this week we're going to be talking about sections 9.3 and 9.5. 9.3 is a second section of applications to physics and engineering. We already saw one of these back in chapter 7. I think that this one's going to be a little bit easier than that one that we saw back in chapter 7 here. We have a much more natural progression to sort of build up our ideas, whereas with work, we were just sort of, in a sense, given a string of like 7 different physics equations that were all easy, but that we needed to kind of smartly string together carefully. Here, we're not going to get too much of that today. I really think that this section, rather than thinking about like the chapter 7 section on physics applications, I think for this section you should think about this a little bit more like arc length, where there is going to be a simple geometry idea that we're going to be able to use our Riemann ideas to upgrade to a more general purpose idea that's going to involve some integration, unsurprisingly. Um, I just think there's a little bit more natural of a flow to our concepts here. So what we're going to do today to kind of walk through this is we're going to look at our two, in a sense, geometric ideas here. We're going to be looking at moments, which we'll define in a bit, and center of mass, which I think is something I don't necessarily need to define too much here. To find the center of mass of a set of objects is to find the location at which their masses would be centered. And the important thing is that they are all not in one location. They all might have different masses. So we're going to get some very good geometric ideas of what those mean first in a 1 and 2D discrete setting. Our goal for the day, though, is to really talk about a 2D continuous setting, right? So let me kind of talk through what I mean by these 3 perspectives here. In a 1D discrete setting, what I mean is our masses can only exist in one-dimensional space, so that means on an axis. So you should be just picturing the x-axis here, and discrete means we have a countable number of objects that we're going to attempt to measure this center of mass in the moments of. And so what that means is really you're just picturing a handful of objects on a line, and we want to identify where is their center of mass. Where would they balance? If they were to be balanced on a balance beam, where would we need to put that fulcrum location? In a 2D discrete scenario, we're going to get a similar sort of thing, except the points can be anywhere in XY space. But again, you should be picturing that we're sort of trying to balance a 2D object on a single point. And we want to know where should we place that point so that the sheet itself or the two-dimensional object itself will be balanced. But in a 2D discrete setting, we're not really picturing a whole object, a whole surface right here, but rather a series of points, right? So we're still saying discrete, meaning it's just a handful of objects, but not necessarily an entire surface. Our goal for the day is to talk about the 2D discrete scenario, which is to say, where should you place a fulcrum, a point of balancing, so that an entire surface, whatever the shape may be, would be balanced to sit there rather than leaning to one side or the other. We want to know where that center of mass is. How could we balance this shape on a single point out there? So what we're going to do is we're going to talk 2 discrete setting cases where we have only a finite number of points. The continuous setting, you should be imagining a whole sheet instead of a finite number of points. You should think of this sheet or this area as an infinite number of points, right? So what we're going to do is our typical thing, which is we're going to do geometry in a finite scenario. Then we're going to stop and think about how our Riemann ideas are going to allow us to extend this to an infinite number of points that each have an infinitely small bit of mass for each of them. But then we're going to use an integral to accumulate all of those masses and distances to find a center of mass out there. So the first 2 bullet points here are just geometry. They're just problems that you might have seen in like a high school physics class. The third bullet point here is really our goal for the day, which is to step those ideas up to an integral continuous scenario to talk about the center of mass of any 2-dimensional object. So that's really our goal here today. So we're going to start with some easy ones, 1D discrete and 2D discrete. that involve no calculus, then we'll use those ideas to expand into a Riemann type scenario with an infinite number of subdivisions, infinite number of points, infinitely small masses, and we'll accumulate all of the moments with an integral to compute the center of mass for any two-dimensional shape. So the 1D discrete scenario first. We have two weights, and we'd like to place them on a balance beam. So the balance beam is balanced. Where the fulcrum is located is where the center of mass is going to be if the balance beam is balanced. If the balance beam is resting like this, then this is not the location of the center of mass because the balance beam is not balanced. In this case, it looks like I would have to move the fulcrum a little bit more this way to balance the balance beam. And if the balance beam becomes balanced, then we can say that this location right here is defined to be the center of mass, right? So the center of mass is the location at which the axis or axes would be balanced given the objects being placed on them. So what we're thinking here is that we've got two weights. One weighs 10 kilograms, one weighs 5 kilograms. I know where object A is located. It's 8 centimeters to the left. What we want to know is where should B be located so that we are perfectly balanced, so that that fulcrum does represent the center of mass. Fortunately, pretty smart dude figured this out a while ago. And Archimedes experimentally came up with what has become known as the law of the lever, which is a really simple relationship between two masses that are going to be on a one-dimensional axis here. And what this is going to end up saying to us is that if we're going to place object A, which weighs 10 kilograms right here, at a distance of 8 centimeters from the fulcrum, what we would like is we would like this thing to remain balanced. And so because object A weighs twice as much as object B, we're going to need object B to be twice as far from the axis as object A. A good experiment that you can do to confirm for yourself that this type of statement is true is to go and attempt to open a door in your house. And what you should do is you should go to an open door, and with one finger, you should push on the open door very, very near, within 1 inch of the open side, of the side that has the handle on it. And you should find the door opens very, very easily. Then you should put the door back in its original position, and you should take your one finger and you should bring it to the other side of the door and place it within 1 inch of the side that has the hinges on it. And then you should try and push the door open. You should see that it requires way more force, and that is because the torque that is being applied with a small radius is much smaller than the torque that is being applied with a larger radius. We're not talking about torque in this section, but a torque is a rotational force. It's what you are applying to the door. You are applying a linear force, which is having a rotational result on that door here. And you can see in this fulcrum situation, it's similar because we're rotating, we're pivoting on that center axis that's right there. So what Archimedes in the law of the lever says is, given two masses, m1 and m2, and two distances, I'm not pressing anything weird. Come on, man. Now let me get, oh, okay, I'm still okay. And two distances from the fulcrum, D1, sorry. I'm going to rename these. I'm going to call these A and B as our subscripts here so that we can associate them with the items A and B over here. So this will be distance A and distance B. The beam is balanced if MADA equals MDB. The mass of object B times the distance that object B is away from the center. And we can see if that's going to be the case right here if we choose to put object B 16 centimeters to the right. The mass of object A is 10. The distance that object A is away is 8. The mass of object B is going to be 5. And notice here, we really should just be solving for that 16 right there. This is our unknown, the distance away that this should be. Over here, we get 80. 80 divided by 5 is going to be the 16 that we're getting for that distance that B should be away right there. So that's how we know that should be 16 units away. So what we want to do real quick here is we want to rephrase this more in terms of an axis, right? When we talk about distances, that's not locations. Distances is the amount of length between two locations. But what would be more useful for us, since we're about to upgrade this into a two-dimensional scenario, is start talking about locations rather than distances. So what I would instead like to do here is redefine some of these locations. If we define our fulcrum location as x bar, this is our center of mass. Bar typically denotes mathematically an average. So this is sort of like an average value location between A and B right here. It's average. It's where our center of mass is. Average is a measure of center, as we're going to discuss actually in tomorrow's video with our mean, median, and mode for probability and statistics. So this is a sensible notation for our center of mass right here. This location here, I'm going to call x sub A. Yeah. And this location here, I'm going to call x sub B, the locations of A and B. So what I kind of want to show right here is that we can generally compute where should the center of mass be. So in general, where is the center of mass? Well, we've got a couple statements to work with here. It looks like what I'm seeing here is that my distance away that A is, the way that we got that was by doing x bar minus xa, right? The upper bound minus the lower bound gave us the overall distance. My distance associated with point B, again, is the upper bound minus the lower bound. Notice it's in the opposite order here. xb is the upper bound, minus x bar is the lower bound. So we've got those two distances right there. But they're now rephrased in terms of locations on an axis, which is going to be very beneficial for us because we're going to need to do things like integrate over x. It's not going to be helpful for us to have distances that are defined in terms of x. We just want the x parts themselves in here. So in general, where is the center of mass located? Notice that what we're interested in finding is x bar. That's our center of mass right there. So what I want to do is just rephrase our centered balance beam phrasing in terms of that. So what we had was that MA dA equals MB dB. Our mass of A is just the mass of A, but the distance away that point A was, we had that here. It's x bar minus xa according to our picture. Mass of B, there's nothing for that. dB was the xb minus x bar. So what I want to know is, where is this center of mass x bar? So let's go ahead and solve for it algebraically here real quick. So I'm going to do some real quick algebra, but it's just algebra right here. I'm going to expand both of these and then solve for x bar. So my first step here is MA x bar. But I'm gonna skip some steps here. I know that I'm going to get an MA xa and I'm going to add it to the other side. I'm going to do that all in one step. Similarly, on the right-hand side, I'm going to get an MB XB. I want that to stay on the right, but I'm going to get an MB minus and times a negative x bar, and I want to add this over to the left. So I'm going to get here an MB x bar on the left. On the right, I've added over the MA xa, and I kept my MB XB on the right. Now I'm going to factor out the x bar and solve. All right, so what we've done here is we've now come up with a general formula for the center of mass of two objects on one axis. All right, this is a 1D setting still right here. And importantly, very importantly, we can write some of these a little bit different right here. Notice that this is the sum of the m sub I, x sub I. And down here, this is just the sum of m sub I. All right, so we've got some special names for each of these parts right here. I'm going to reference my notes here because we do get a bunch of names and a bunch of notation here today. And so we refer to this guy right here as, now notice, I'm going to come back to our picture real quick before I write this notation because this is a little bit weird right here. You should notice that in a sense what we were doing right here was what when we made our measurements of XA and XB, that was really a distance that we were away from the y-axis, right? So you should notice here that this rotation is really about the non-existent y-axis that we're experiencing right here. And so in general, we would refer to this as the moment about the origin. But we're going to see in a bit that we're going to, in a two-dimensional setting, that we would think about that as um, the moment about the y-axis that we've just computed, because those distances were distances from the y-axis. They indicate our rotation about an axis that's sitting on the y-axis right here. And so in general, we want to define some of these words with some physics words right here. Um, our moment in this case is our sum of our m sub I, x sub I, and this is the same thing. I just want to just maybe do this. Just do that. There we go. The moment is our moment of the system about the origin in this case, because we don't have any other axis of which to reference right here. And our center of mass in this case, we have determined our center of mass to be this statement here, x bar equals the sum of the m sub I x sub I over the sum of the m sub I. So in this case right here, this is the moment about the origin divided by the total mass. So what we're going to do is we're going to extend these ideas now to a 2D discrete scenario, right? We solved this super basic problem here of saying, based on Archimedes' law of the lever, that we should be twice as far away if we only weigh half as much to make this be balanced. This just says there's a linear relationship between distance and mass when we're attempting to slide things along a balance beam here, a fulcrum. Importantly, we reorganized our information. Archimedes' law of the lever is about distances, but we really want to be talking about locations instead of distances. So we marked some values, thinking of this as sort of like an x-axis here, so that we could rephrase distances that law of Archimedes or the law of the lever comes in terms of locations that we're going to actually need to be using for our upcoming computations here. But in general, recognize that a moment is the sum of the masses times their locations here. If our moment sums to 0, then that says that our center of mass is symmetrically located where equal amounts of stuff are to the left and to the right there. Let me see if I forgot anything over here. So this is our unexciting one. So I am going to just move on to our 2D discrete scenario here. So let's suppose that we have 3 particles in xy space, and we would like to find the center of mass of those 3 things. So what we now need to talk about is having this moment about the y-axis versus a moment about the x-axis. And so the way that we're going to define this is just like we had before. The moment about the axis was a mass times a distance. But up here, distance was kind of arbitrary because we only had one axis in which to measure distance. In a 2D setting, we now have 2 axes in which to measure distance, so we want to be a little bit more careful about it here. So our moment about the y-axis is going to be our mass times the distance from the y-axis. And notice that in this case right here, so we're going to denote this m sub y. It's our moment about the y-axis. But notice that the distance from the y-axis is x. X is how far you are from the y-axis, right? So this is going to be the sum of x sub I, m sub I, x sub I right here. It's our x distances, because that's the distance from the y-axis, times our masses right there. And therefore, if we are looking for our y coordinate of the center of mass, we'll call that guy y bar. And just like we got before, oh, sorry. Sorry, I'm getting my x's and my y's a little bit backwards right here. Right. So I think I kind of actually phrased this poorly right here. What I'm going to do is I'm going to change this to x coordinate, which is what this really should be. So notice what's happening here. If we're talking about our moment across the y-axis, then all of the distances that we're measuring are x distances, because x is how far you are from the y-axis. If this is the case, then what we're looking for is an x location for the center of mass out of our moment about the y-axis, because that's telling us how far are you from the y-axis. We're getting an x distance out of that. So the x coordinate of our center of mass right here that we're going to get out of this is that the x-coordinate of the center of mass should be our moment about the y-axis divided by the sum of the masses. And very, very, very similarly, I'll have to make my same adjustment right here. If we are looking for the moment about the x-axis, then we're interested in distances from the x-axis. Your distance from the x-axis is your y-coordinate. So this is where we're going to get our m sub x. Our moment about the x-axis is going to be the sum of all the masses, but we're measuring y values because your y coordinate is how far you are from the x-axis. Therefore, the y coordinate center of mass is m sub x over the sum of the masses. And again, notice that this is sum of m sub I, y sub I, over the sum of m sub I. And I'll write the same thing up above here. All right, so the x bar stuff is the sum including x. But when you're measuring x distances, those are distances from the y-axis, which is why that's referred to the moments of y right there. So the moment about the y-axis. So realize, and you just watch me get variable confused right there. Pay attention to that so that you don't yourself get variably confused here. So let's go ahead and find the center of mass of three of these objects here using this formula that's been given to us. So we've been given three objects, A, B, and C, and where we can see it, they're located. They're all in the first quadrant. So I'll give myself some first quadrant stuff. I can see that our furthest coordinate is at 10, so I'm just making axes go out to 10 here. All right, so first object located at 2, 1. There's A. Second object located at 6, 2. There's B. Third object located at 4, 10. There's C. So here's the thing that I'm thinking. What we know is that object A weighs the least at 2 kilograms, so it's going to have the least pull for the center of mass. Object B weighs 4 kilograms, so it's going to have twice as much pull for the center of the mass as A does. So if it were just between A and B, I would expect it to be more like right here, like a third of the way from B, but half or 2/3 of the way from A, because B has twice as much weight. You can almost think of this as like a gravity type situation right here. Right? Finally, C weighs a ton, right? C weighs 6 times as much as A and 3 times as much as B. So this is really leading me to believe that I should be estimating our center of mass being somewhere way up here, right? This is maybe my guess right here. I'm guessing it's going to be something very close to C because C weighs the most, right? So it's going to have a heavy weight on the beam. So we don't need to be as far from the center of the beam to balance with these other two things that are going to be a bit further away out there. So my guess, at least I can make a good Y guess, which is that it should be somewhere around like 7 or 8 up there because there's so much more drag from the C term because it weighs so much more. So let's go ahead and find the center of mass of these three objects right here. So we have that I guess I'll call them MA is 2, MB is 4, MC is 12, and we have that point A is 2, 1, point B is 6, 2, point C is 4, 10, and I can go ahead and compute my center of mass here. My x bar, the x value of the center of mass, should be the sum of the m sub I x sub i's over the sum of the m sub i's. So in this case, it looks like we're going to get the first mass and the first x value added to the second mass, second x value, added to the third mass and third x value. Here I'm going to get 2 times 2 plus 4 times 6 plus 12 times 4. And we're all going to be divided by the sum of the masses. 2 plus 4 is 6 plus 12 is 18. So it looks like I'm getting 4 plus 24 plus 48 over 18. That's 28, and 48 is 76. And 76 over 18, I'm getting 4.2 repeated here. Similarly, for the y bar, we can do the sum of the m sub I y sub i's over the sum of the m sub i's. I already know that denominator is going to be 18. That didn't change. The first mass is still 2, but the y coordinate is now 1. The second mass is 4. The y coordinate is 2. Notice these small influences from those 2 points. The third one is a huge influence from the third point up there. So I'm getting 2 plus 8 plus 120. So look at how much more influence that has on the y value than the others. There's going to be 130 over 18, and that's going to give me 7.22222. And man, I nailed it on the y value for my guess right here. I feel pretty dang good about this guess, actually. Man, my guess was actually really good right there. It looks like my guess is directly centered above 4. And I guess I should have known that it should have been a little bit more toward the B direction right there. But man, my guess is actually that dot needs to be moved like 1 dot's width to the right, and I pretty much nailed it right there for our location of the center of mass. So let me just say, that was pretty dang close. So it's good to do these guesses, by the way. It's always encouraged for you to guess first, so that when you get an answer, you can feel good about the stuff that you got right there. So what we just did is we find the XY coordinate location of the center of mass of these 3 objects right here. If you imagine this being like 3 planets out in space, this would be the location that you could sit at and feel exactly no gravitational pull. If these are the only 3 objects gravitationally acting on you, this is right where all of their gravities would perfectly cancel out, and you would not be directly pulled towards any of the planets. You would sit there perfectly still in space, which is unique. Any other place in space, you'd be close enough to one of these objects to experience its gravitational pull more than the others and to be pulled towards it. This would be sort of like our dead point in space right there, equal pull in all directions. So what we've got here now is we've got this idea that we use these moments to help us compute center of mass locations. We can see that these moments are sums, and sums should lead us to think about integrals when we have more and more and more parts that are being broken down more and more finely. So let's talk about now our 2D continuous scenario, what we're actually here to do. Suppose we have a 2D surface and we'd like to find its center. Here we should think of a surface or an area, a two-dimensional object, as an infinite number of points that are infinitely close together. And that means we should be thinking some sort of Riemann thoughts here. So what we should do is we should do what we always do, and let's consider a general area and subdivide it into typical Riemann sticks, right? So I'm just going to think of any old curve out there from A to B. And let's do our typical subdivision into Riemann sticks. What we know is that what Riemann stick choice we make does not directly matter so much. But we're going to have an important thing that we want to do with this guy here because we are looking for centers of mass. So what we want to do here in this case is we would like to find our strategy for this guy is this. What we really have here is an infinite number of points that are out here in this solid. But what we can do is if we approximate this solid as a bunch of rectangles over here, then with a rectangle, we should be able to very easily find the center of mass of each rectangle. Right? Hopefully you guys agree with the center of mass locations. So each of those dots is representing the center of mass of that Riemann stick. So what I want to do here, my strategy for this guy is to say, listen, I know there's an infinite number of points and I can't directly deal with an infinite number of points. But what I can do is I can lump them all into groups, rectangular shaped groups. Because what I am very confident about is that the center of mass of a rectangle is just the center of the rectangle, right? The average x value and the average y value of that rectangle. It's a very regular shape, it's a regular solid, and therefore it has very easy to define features like where is the center of it located. You should obviously notice that this region A right here does not have an obvious center of mass in either the x or y direction because we don't have a uniform distribution of stuff in the x direction or in the y direction. It changes over time based on the height of the function. But in a rectangle, I do have a uniform distribution of the x content and of the y content, and so it's easy for me to make the claim then that it's going to be halfway along the x stuff, halfway along the y stuff. That's just the middle of the rectangle, right? So a very important, but I think very simple statement for us to make here is the centroid of a rectangle is the center of the rectangle. The center of mass of a rectangle is just the center of the rectangle. So what I'm seeing here that I can do for my strategy is suppose that we, for example, in this example here, what do I got? I've got 6 Riemann sticks already. So maybe it looks like I'm doing a 12 Riemann stick subdivision right here. An approximation with n equals 12, maybe 12 subdivisions. I could find the 12 centers of masses of the 12 Riemann sticks and then just go back up and perform our 2D discrete scenario right here and just have an answer, and it would be a very close estimate. Obviously, what we're going to do in any Riemann scenario is then imagine that we take this limit as n goes off to infinity, but still this idea is retained, which is that we're going to handle a grouping, an infinite grouping of points together as one rectangle, because one rectangle should have a known center of mass. So we can say, take these points and know their center of mass, take these points and know their center of mass, take these points and know their center of mass, then use our discrete technique to find the overall center of mass of those objects, of those masses right there. We want to talk about what is the center of mass of each Riemann stick, and then use our 2D discrete technique to find the appropriate weighted average. And I literally mean weighted average in this case because they're weighted by the masses of each object. You should notice that each of these sticks probably has a slightly different mass than one another. This is a smaller stick, smaller mass. Taller stick, taller mass, more mass. Tallest stick out of the ones that I drew, this one should have more mass than all the rest, and therefore a little bit more pull for its associated with its center of mass here. That weighted average is going to be weighted a little bit more towards the ones that have more weight, the ones that have more mass. So let's go ahead and see if we can kind of apply this technique. I'm going to draw a more blown up picture before I do this here. All right, so notice that what we're doing here is I'm just drawing one Riemann stick. It goes from the x value of x sub I to x sub I plus 1. And I know this centroid is going to be located at the dead center of this thing right here. So another thing that I'm going to do that's kind of sort of important here conceptually, but is going to have no computational distinction for us whatsoever, is that it looks like I'm setting up my Riemann sticks to be associated with our midpoint rule right here. So what I want to know is where is this centroid located? What is the centroid of the ith Riemann stick? Well, all I'm really asking is what's its x and y value? So what I can see here is that the x value that's associated with this is halfway between x sub I and x sub I plus 1. Well, we've already defined that in a previous, when we talked about our midpoint rule stuff. It should just be the average of those, of the two subsequent terms right there, right? So x bar sub I is what I'm going to refer to as this x location. It's halfway between x sub I and x sub I plus 1. So the centroid of this thing should be located at x bar sub I. That's the average of x sub I and x sub I plus 1. What is the height of the centroid? Well, the height of the whole thing is f of x bar sub I, right? The height of x bar sub I. But I only want to keep half that height, just like we only kept half the width right here, right? So this should be half of the output that you get from plugging in x bar sub I. Right? So we'll call this location C sub I. It's the ith centroid of all of our Riemann sticks, is located at halfway between two x values, and then half of the height associated with that one given x value right there. That's just the middle of a Riemann rectangle. So this is a general centroid of a Riemann rectangle right here. That's a little unfortunate there. Whatever. So there's our centroid location. Next up, we need to know what is the mass of each of the objects right here. And what I know is that mass is closely related to area. There's just one other term that we need to know that goes with this. Mass is the density times area, right? Just a pretty general formula right there. Density is mass per unit area times area, just gives you back mass. So in this case right here, we're going to be able to say that m sub I equals rho times the area here. And what is the area of one Riemann stick? Well, the area of this Riemann stick is a Riemann stick with width here is delta x. And what is the overall height of the Riemann stick? It's f of x bar sub I, because we're measuring those things at those barred heights right there. So I'm going to get here delta x times f of x bar sub I, right? So this is the overall mass of a single Riemann stick. It's the density of the Riemann stick times the area of the Riemann stick. It's just a delta x times an f of x, but we're measuring that height from that middle location right there, so it's the x bar sub I. It's halfway between x sub I and x sub I plus 1. And so now that we know the location, we've got the mass of the ith Riemann stick, and so now we can talk about the moment about the y-axis of one Riemann stick. The moment about the y-axis is always the mass times the distance from y. In this case, we've got our mass is that rho times delta x times f of x bar sub I. That's our mass term. And what is our distance from the y-axis? In this case, our distance from the y-axis, this right here, is our centroid's y location right there. We decided that our distance from the moment, right, to here was only 1/2 of x bar sub I. And so that's exactly what wait a minute. Oh, I'm measuring the wrong one right here. Our distance from this x-axis that's sitting out here, right? Our distance, sorry, I'm saying the wrong thing and thinking the right thing. Our distance from the y-axis, that's what we're measuring. Distance from the y-axis. Distance from the y-axis here is just x bar sub I. It's exactly the x location of our centroid point right there. And so that is just our x bar sub I. And so now what we want to do is we want to sum all of these moments about the y-axis, right? We're adding up all of these things, but we're also going to, I'm going to say here, and let n go to infinity. And what you should see is that we're just adding up a bunch of terms that are going to be representative of an integral to us here. We're going to do the integral from a to b of rho. It looks like delta x is going to turn to dx. It looks like we've got an f of x right here term. It's just the height, because that bar, remember, is halfway between 2 points that are now infinitely close together. So now there's no distinction between x sub I bar, and x sub I plus 1. Those are all infinitely close together now, so those subscripts are no longer critical to us. We're going to cover all x values from a to b are going to get represented. And it looks like we've then therefore got an additional x on the end right there. And so just cleaning this guy up a little bit now, we're going to go ahead and say our m sub y is, it looks like the rho can get pulled out front for density, integral from a to b of x f of x dx. So there now is our formula that we're getting by adding up the masses times the moments of all of our Riemann sticks, and then allowing the number of Riemann sticks to go to infinity. Now, the interesting thing here is that this is not symmetric. The formula that we're going to get for m sub x is not going to match this formula right here, and that's because this distance x sub I is no longer going to be a good sensible way for us to phrase our measurement for us anymore. If we want things in terms of x, I can't just go using y sub I as my next point right here, so we're going to get a slightly different phrasing for m sub y. And so let's do our same kind of deal here again. Before we did this, we said the moment about the y-axis was the mass times distance from y. It should now be the mass times the distance from x. I'll say from the x-axis here. Notice now that the distance from the x-axis, well, that's just half of our height right there. This right here, that's our c sub y, like I was trying to say a second ago. How far are we from the x-axis with one of these Riemann sticks? Our distance from the x-axis is half of f of x. It's half the total height of the Riemann stick right here. So again, kind of following our pattern from before. Our mass is still going to be rho times delta x times f of x sub I bar. That's the mass of every single Riemann stick. But the distance from the x-axis is different than the way that we measure the distance from the y-axis. Here, our distance from the x-axis of that the center of mass of that stick is half of that function value height halfway in between right there, the x bar value. And so now if we want to add up all these moments about the x-axis, and we'll say again, and let n go to infinity, then here we're going to find that we're just going to get the integral from a to b of all these parts here. Rho delta x f of x 1/2 f of x. Now let's just rearrange these so this looks like something we might actually want to deal with. The thing that you should be noticing is that the rho is a constant, the density. 1/2 is a constant. Oops, by the way, this guy right there should be our dx, or delta x. So I'm going to get this rho over 2 is going to come out front. Integral from a to b. It looks like dx I'm going to put on the end, and it looks like we've actually multiplied f of x twice. So here is our moment about the x-axis right there. Right, so notice that these formulas didn't pan out the same, and that's because one of them had the height f of x times the width x. One of them had the height f of x times the height half of f of x. So that's why we're getting a difference in the formulas for m sub y and m sub x. It's because when you're measuring the xy location of the centroid of a Riemann rectangle, the width out here is just x. The height is f of x. So here we multiplied by an additional x. Here we multiplied by an additional f of x right here, or half of f of x right there, since it was only half the height, because we're looking at the centroid of the rectangle right there. So finally, very importantly, we can now determine what the center of mass location is going to be, and this will be easy because we, in a sense, already did this in our 2D scenario. In our 2D scenario, we just said that the center of mass for the x location should be our y moment divided by the sum, or by the total mass here, or in this case, we'll think of this as the total area. Our y bar then was going to be the m sub x over the total area here. And so notice, by the way, that if we think of area, A is area, this should really just be the integral from a to b of f of x. It's just the actual entire area of the thing. That's all of the mass that we're going to be accumulating out there is going to be all of that stuff in the area down there. And so in total then, it's typically phrased as x bar equals 1 over a of, and x bar is associated with our m sub y. So that's this guy up here. It's the x f of x version. Our y bar, same thing, will be 1 over the area times rho over 2 integral from a to b f of x squared dx. Right? So we've got our formula for the center of mass now, for each of the coordinates of the center of mass of any object. Holy cow. Let me just try Oregon over again right there. My goodness. Can't draw a box these days. Here we go. So we've got our two center of mass formulas. So let's go ahead. Oh, didn't I just state this stuff right here? I did. Okay, whatever. I got ahead of myself. That's fine. Where's the, did I not, what? Seriously, did I? Okay, I thought I typed that up. That's okay. We are going to find the center of mass of this object from number 36. I think it's 36. Is it 36? All right, so I'm going to draw you an object, and we're going to find its center of mass. Our object here in number 36 from the book, we're going to go 1 in each direction here. So notice this is an overall width of 2. We're going to get a semicircle shape on top. Hey, nice semicircle there, Tony. And we're going to get a box down here. So here's our object. It's got a semicircle top. It's got a square bottom. All right. So notice here at the top is a semicircle. The bottom is a square. So I'm going to use my same general idea that I used in the building of our formulas here, which is I want to think about how I can do this most simply by breaking this down into shapes where it's easy to find the center of mass of each shape, then use our 2D discrete ideas to, in a sense, do the weighted average of the centers of mass of each object. So I'm just going to refer to this as the top and the bottom, and I think that we're going to find some pretty easy stuff right here. So first things first, I might say that my equation that governs this top shape is x squared plus y squared equals 1, which we might rephrase as y equals the square root of 1 minus x squared. And we're looking at this on the interval from -1 to 1. And I might ask myself right away, do I know the center of mass of this top part already? And what I'm thinking is, I see that we're perfectly left-right symmetric. If we're left-right symmetric, then that must mean that our center of mass is halfway between the left and the right values. And so I already know that x, I'll call this x top bar equals 0. So I am looking for the center of mass of the semicircle and the center of mass of the square, and then we'll perform our weighted average on the two. And so I really need to find two centers of mass to find the one overall center of mass. But notice I've already even got one of my parts right here. So let me at least say y bar of the top. We don't know. We'll have to do some work for that guy. What else do we know about the bottom here? Well, it looks like our equation of interest is y equals -2 as x goes from -1 to 1. But notice that this is just a square. A square is a special case of a rectangle. We've claimed that we already know where the center of mass of any square is, and it's going to be located right at its center. That's not, I don't think I'm blowing anybody's mind by that. Again, I know this center of mass in the top is going to be left-right split. I know it's going to be on the y-axis somewhere, but it clearly should be a little bit closer to the bottom than the top, since there is more mass on the bottom of the semicircle than there is in the top. But I don't know about where, but I'm guessing it's going to be something like this guy right here, but it's unclear where. So I'm pretty sure that I know my x bottom and y bottom already. I don't think I need to do any math for these guys right here. I think the center of mass of the square, I think the x value is 0, and I think the y value is -1. I don't think I'm blowing any minds by saying the center of mass of a square is at the center of a square, and we can really easily see where it is right now. So it looks like all I need to do, the only thing I really need to do work for, is to find the center of mass about the y value center of mass, the y coordinate of the center of mass, for just the semicircle, and then we'll be able to combine our two ideas right here. And by the way, even further notice, I know that my final x value for the center of mass is also going to be 0. This whole thing has left-right symmetry. Really, our only question that we're asking here is what y value is going to be the location of the center of mass of the entire object here. It's the only part we have to worry about. Um, Let me just say that. I can just by visual inspection. So all we need to go hunt for is just a single y bar. Out of the 4 points that we needed to identify to average, we only need to actually do work to get one of them right here because symmetry handled the other 3 for us. So I'm going to go remind myself of my y bar computation right here. Here it is. Y bar should be 1 divided by the area times rho over 2. Let's see, y bar is going to be 1 over the area times the density divided by 2 times the integral from a to b of f of x squared dx. That's all we got right there for our formula, right? So we need to do 2 things. 1, we need to evaluate this. 2, we need to evaluate the area right there as well. Finally, I was given that rho is 5, so we can go ahead and slot that guy in. First here, let's notice that this area is just 1/2 pi r squared, where r is 1. So this is just 1/2 pi, or pi halves. I already know what the area of my shape is. Typically, you will probably need to do integration to get that area right there. I had a known geometric shape, so I didn't have to do integration right there. But often, if you're looking for that area, it's going to be that integral from a to b of f of x. So it looks like I know in my case here then, I have 1 over pi halves times 5 over 2 times the integral from -1 to 1 of square root of 1 minus x squared dx. This looks pretty dang manageable to me. I'm seeing here that multiplying by 2 in the denominators makes those cancel. That's going to leave me with 5 over pi times the integral from -1 to 1 of just 1 minus x squared. Hopefully you understand that this is now very easy for us here. We're going to get an x minus 1/3 x cubed from -1 to 1. And I'm going to be getting here 1 minus 1/3 minus -1 plus 1/3. That's going to be 2/3 plus 2/3, which is 5 over pi times 4 over 3. And so I'm getting 20 over 3 pi is going to be that y value center of mass for just that top. But isn't that going to be... Am I being a little dumb right here? What's my... So my issue that I'm landing at right now is that I am getting a number that's like 2, and 2 is way up here, and it's clearly not the center of mass of this object that's sitting right there. So where am I going wrong here? This is a circle of radius 1, so this is x squared plus y squared equals 1. I subtracted x squared and took a square root. It is the top half of the circle, so I kept the plus. We're evaluating from -1 to 1. I know I'm only interested in my y value for my 1/2. We're doing our squaring. 1 divided by the area. The area here is definitely pi halves. I know that the area is pi halves because this is half of a 1 radius circle. It's half of pi r squared. It's half the circle. R is 1. It's half of pi, pi over 2. We can also think of this as 2 over pi times the density. Is that where I'm getting my... Oh, I see what I'm doing. A little bit dumb down here. Okay, okay, okay. Let me show you my little mistake that I'm making. So the mistake that I'm making right now is dealing with rho, and I'm now realizing that I said some words up top here that were a little bit wrong, so let me back it up a little bit. What we really wanted down here was actually area. And what we know, or sorry, what we originally defined this to be is that we're dividing by our, well, so let me scroll all the way up here. When we were talking about our original moment, we were dividing by the entire mass. Mass is going to be density times area, not just area. So let me fix this stuff right here. We should have that our mass is density times area. Notice that each of our moments both have a rho up in the numerator. We also have a rho in the denominator here. So maybe let me just do this to help us fix this guy. Am I too close to the bottom? Yes. Let me see what happens if I try it anyway. How angry is it going to get at me for that? Not very. That worked out excellently, actually. So really what we want to say here is that x bar equals our rho AB x f of x dx over rho A. Rho times A is the mass of this thing. It's the density times the area. And we're going to get that those densities are going to cancel. And so I'm getting 1 over A integral from A to B x f of x dx. And that makes sense because if the density is uniform everywhere, then the density shouldn't have an impact on where your center of mass is. Similarly, for y bar, we should have been getting rho over 2 integral from A to B of f of x squared dx divided by the mass. The mass is the density times the area. The rho's are going to cancel, and we are going to get here, I guess, a 1 over 2a integral of f of x squared dx, right? We're dividing it by, we have 1/2 of it, and we're also dividing by a, so like a 1 over 2a down there, half as much. Okay, now with this light update here, that basically means to me that all I need to do is this. How many times do I need to press end, yo? And now we are finding this to be y bar equals 1 over pi times 2/3 plus 2/3. That's going to be 4 over 3 pi. And when I do 4 divided by 3 pi, I'm getting 0.4244. All right, so let's keep that area mass distinction square there. I made a mistake right there. I just went with straight up area when I should have been using mass. Mass is density times area. Our density terms canceled. So let's kind of review where we're at right now. Here's our two parts. We just determined that this one, as expected, is a little bit lower than half, right? So I found that my x top bar and my y top bar. My center of mass for the top parts was 0, and the y one was the point, or I'll just call it what it was, 4 over 3 pi. We found that for the bottom parts, it was much easier. The x value was 0, the y value was -1. It was just the center. What I need now is I need the mass of the top and I need the mass of the bottom so that I can compute my overall center of mass. The mass of the top should be the density of the top times the area of the top. That should be 5 was our given density. The area of the top is pi halves, because that's half of our circle. So 5 pi halves is the mass of the top part. The mass of the bottom part is our density times our area. Density is 5. Our area of this square down here, notice that it's a 1 radius circle. So that's a 1 and a 1. The circumference is 2. That's a side length. So our area here is going to be 4. So that's got a total mass of 20. And so now that I have my center of masses, the centers of each mass, and I have the masses associated with each mass, I can now go ahead and find my overall x bar. So I know that x bar is 0 by symmetry. My overall y bar should just be the moments of the two, the y times the m plus the y times the m. So my weighted average right here. I've got the mass of the first thing is 5 pi halves. I've got the y value of that top part is 4 over 3 pi. I've got the mass of the second part is 20, and I've got its y value of -1 for the center of mass. And we're going to divide that by the sum of the masses, which is 5 pi halves plus 20. And all we got to do is go to our calculator here, and we are good to go. I'm at least noticing there's a little bit of convenience right there. So it does look like we're getting 26 minus 20 over, 5 pi halves plus 20. I don't want to simplify that guy at all right there, but let's go ahead and get what our y bar center of mass location is going to be here. I've got 26 minus 20. It's going to give me -16.67. And we're going to divide this guy 5 pi halves plus 20. And we're going to get our 16.6667 is going to be divided by this guy right here. And I'm getting -0.598. So it looks like the overall center of mass of this object then is going to be located just below the x-axis here. And I'm going to draw one last picture so we could just kind of confirm that this seems sensible to us. The reason why this seems to make sense to me is because the square is clearly taking up a lot more area than the semicircle is. And so the center of mass is going to be a little bit closer, right? We had our first center of mass was there, our second center of mass was there. And what we're finding is that we're going to be a little bit more than, so this distance right here from top to middle is 1. And we're going down about 0.6 right there. So our final answer is this guy right here. So this is our top, this is our bottom, this is our overall right there. And I think that's pretty believable to me right there, because we should have more of a y value influence from the bottom parts than from the top parts right there, because there is more area down there. There's uniform density everywhere, so the density doesn't come into consideration right here. So notice that finding center of mass is really, really helpful if you can identify some symmetries and identify any geometric shapes that you already know. There's a bunch of places here where we got to skip steps because we just kind of knew a part going into this, right? When we set this problem up here, I knew that left to right right, I know that the center of mass, this has to be on the y-axis. That's half the whole problem is done right there. That says to me, I already knew the center of mass for the top, knew the center of mass for the bottom. I even knew the top to bottom center of mass for the bottom square piece because it's a square. It's a uniform shape right there. It has the same stuff on the top as it does on the bottom, and therefore it's easy for me to say then it's halfway in between because it's uniformly distributed. The y parts, the strips, how much area is accumulated in a semicircle, change as y changes. And so it wasn't directly clear to me what y value we should be getting for that center of mass. So we did apply one center of mass formula out of the 4 parts that we wanted to get the y value center of mass. Then we applied our discrete thoughts right here to say, now we're thinking of this solid as really just 2 points in space. We've simplified from 2 entire surfaces to just 2 point masses, as they're called in physics. Point masses meaning they have no like area themselves. They're just masses floating in space. So we found sort of, in a sense, an equivalent point mass that's associated with the 2D surfaces, and then found the center of mass of the 2 discrete point masses that we came up with right there. So a lot of these problems are about recognizing symmetry, recognizing geometry, breaking problems down into a finite, discrete, countable, manageable number of cases, and then dealing just with those manageable cases in a discrete way. So even though we started with those like simple settings of the 1D and 2D discrete, those are actually still directly used when we're doing our continuous scenarios, because as you saw in this case right here, we want to decompose any shape that we have into small groups of sensible, easy to manage shapes. If I have 2 or even 3 or 4 or 5 individual center of masses that I want to find the overall center of mass for, that's really freaking easy. It's just a weighted average is all that we did right there to find that. So decompose the surface of interest into any number of regions to your convenience, because this last step is just taking a weighted average. It's always super easy. What you always want to do is set yourself up into situations where by decomposing this, you have some simpler equations, simpler regions to discuss. If you can decompose this into some regions where you just straight up know the center of mass because it's something regular like a square or rectangle or even a circle, great, do that stuff. Decompose hard problems into easy problems is really what we did here. We broke down a hard problem, the whole thing, into 2 easy problems. One where we already knew the answer, one where we knew half the answer. We did the work just to find the 1/2 answer we didn't know, and then we combined the answers that we had overall to get our final answer here. And so I guess I would say, to conclude, we would say that x bar, y bar equals 0, negative 0.59836 right there. And there we go. We've used our moments to calculate our center of mass. So all you need to remember about moments is that a moment is the sum of the distances times the masses. And that if you ever want to compute mass, it's always going to be the density times the area, or the density times the volume, whatever your unit of measurement is going to be with that. So there we go. I think that's kind of like the hard one that I wanted you guys to look at right there today. And it wasn't even that hard. Some of the other ones back there are a little bit tougher. I am going to suggest that you do some of these in the homework, but when you see the ones in the homework, they're going to look a lot like this one right here, and you're going to see similarly that you can decompose these to do little to no calculus associated with these guys if you can get away with it right here. So I think your biggest challenge with this section is keeping your x stuff and y stuff straight, since our formulas are not the exact same. You need to know, are you looking for your x or y center of mass to know if you're doing our x times f of x in our integrand, or if we're doing our f of x squared inside of our integrand. Keeping those straight, I'm sure, will be a little bit of a thing for some of you. But other than that, I think that these are pretty straightforward. And like I said, I think this is, for those of you that get nervous about like physics applications, I think this is a much more palatable, easy to grasp thing here. Our only kind of physics thing that was thrown at us is that mass is density times area. And I think that just a little bit of units can convince you of that one. So that's all I've got here for today. I guess maybe my last thought, since I know I like to do last thoughts all the time, is I don't plan on asking you any hydrostatic pressure and force questions right there. I'm much more interested in moments and center of mass is the questions I'm interested in you being able to answer. So out of the 3 topics in this section, those are the 2 that I for sure care about. So I'm going to see you guys in our next video for probability tomorrow. Hopefully it will be live. We will see. Happy introduction to week 9, everybody. See you for the next video.